Hello. So in this example, we want to determine whether this function is differentiable at the point x equals 1. So remember, to be differentiable, there's two things that there's one thing we need to check, but it sort of has multiple pieces. So overall, what we really want to know, right, is whether or not the definition of the derivative, which is a limit, whether that limit exists, right? But we also need for the function to be continuous. So not only do we need the limit to exist, but we also need that the function is defined at that point, because you can't really be tangent to a non-existent spot on a function. So typically the easiest thing to check right off the bat, which is always a good thing to check, but at the same time it's usually very quick to see that it's not a problem, usually. But the first thing and easiest thing to check is whether or not the function exists there. So that's going to be the first thing we check. If the function exists, then we move on to the next step. If it doesn't, then we're already done. That's why it's a nice, quick thing to check first. So we want to check whether or not the function exists at 1, so plug in 1. So f of 1 equals what? So this is 1 cubed minus 1 over 1 squared minus 3 times 1 plus 2. So simplifying, I get 0 in the top, that's fine. In the bottom, I'm going to get 1 minus 3 plus 2, which is 1 and 2 is 3, minus 3 is 0. So you may look at this and think, oh, 0 over 0, we need to factor and cancel the common term and all of that. But remember, we're not checking a limit. That would be if we were looking at a limit. Here we want to know whether or not the function exists. So the fact that we're trying to divide by 0 tells us that's a domain restriction. So since it's a domain restriction, i.e. the function doesn't exist at that point, f is not differentiable. We're done, right? It really is that easy in this case. Now granted, most of them, right, most problems that we're going to tackle aren't this simple because they'll still exist. We have to check other stuff. But this is why we check this first, because if that part is done, we don't have to do any more, right? So no need to go and do limits and the calculus and all of that stuff if we can just sort of short circuit that by checking this. So that's that. Hello. So in this example, we are going to see if this function is differentiable at the point given. So we have this function, this big piecewise behemoth, and we want to know, is it differentiable at 2? Okay. So as is sort of normal, we want to determine, okay, is the function continuous at 2? And if it is continuous, does the sort of left derivative and the right derivative agree? Meaning we would check the difference quotient from the left and from the right. Okay. So checking the first bit, in fact, looking at this, sort of, I don't even have to really write anything down, because if I'm going to check if f is defined at 2, well, we look through and see, okay, is 2 included in one of these pieces, right? So I have minus 5 less than or equal to x less than 2, so it's not in there. But then we also have 2 less than x, so it's not there, and it's not in the other pieces, so f is not defined at 2. So f not defined at 2 so f is not differentiable at 2. Okay, so that's enough. Like, I've already finished. But for the sake of sort of completion, let's pretend for a second it was differentiable at 2. How would we do the left and right pieces, right? So we would need to know, so like assuming this is continuous, which it isn't, but if it were continuous, how would we determine the left and right derivative piece? Well, remember the derivative, right, is this limit as h goes to 0 of f of x plus h minus f of x over x plus h minus x, or just h. So when we say left and right derivative, what we're really saying is h going to 0, say, from the right versus from the left, right? So if I look at this as h going to 0 from the right, that means I'm a little bit bigger than 0. So that would put me in this line, right? So then I would plug in the f using this as my f, right? So I would have that this is the limit as h goes to 0 from the right of f of x plus h, where f of x is this x minus 5. So this would give me x plus h minus 5 minus, again, f of x now, so x minus 3, x minus 5. Sorry, I was getting ahead of myself. I don't want an x here, right? Because I'm forgetting sort of the key part here, which is that my x is really 2, right? So it should be 2 plus h. And this is minus 2 minus 5. Right, so this x is this x, and then this f is this f. Okay, all over h. So now I can continue on. So here I'm going to have 2, so this is the limit as h goes to 0 from the right of 2 plus h minus 5 minus 2 minus minus, so plus 5 all over h. And looking at this, I have a 2 and a minus 2, so those will cancel. And I have a minus 5 and a positive 5, so those will cancel. So I'm going to get the limit as h goes to 0 of just h over h. And those cancel. So I get the limit as h goes to 0 of 1. And sort of regardless of what h is doing, 1 is going to stay 1, right? It's a constant. So this is just 1. So this is telling me the derivative, or the rate of change from the right, is just 1. So then we would do the same thing from the left. So we'd say, okay, limit as h goes to 0 from the left of f of x plus h minus f of x over h, where again, these x's are really that x, but now f is going from the left. It's a little bit smaller than 2, so that's going to put me right over at this first line. So now my f is this minus 2x plus 1. This is going to give me the limit as h goes to 0. Oh, I just realized these should have been from the right, not that it would have mattered at that point. So h going to 0 from the left, so now I'm going to plug in, right, 2 for x, and it's going into that negative 2x plus 1. So my first one then is negative 2 times 2 plus h, right, where the 2 is getting substituted for the x, h stays the h, and I'm looking at that negative 2x plus 1, so I have plus 1, minus negative 2, and now it's just x, which is the value of 2, right, because that's what I'm looking at, plus 1 all over h, which is the limit as h goes to 0 from the left. So now I'm going to sort of distribute everything out and try to simplify as much as I can. So I'm going to get minus 4 minus 2h plus 1. So that was expanding, right, the minus 2. Minus 2 times 2, so that's going to be plus 4 minus 1 all over h. And now again, I can go through and cancel. It's worth noting that because of the way that the difference quotient is designed, it's very common, even when you have concrete numbers, that terms at this point will just cancel nicely. So it sometimes is easier than just trying to like do a running addition of all your terms to see if you have the same term but a different sign and cancel them out directly before you start trying to add up what's left. So here I have a -4 and a +4, so those cancel. Here I have a +1 and a -1, so those cancel. I can't just cancel h right away because this is the only thing in the bottom, so I have to make sure that the only thing that survived on the top has an h in it. So it's good to sort of write out that part before you cancel the h. But here indeed I have just -2h over h. And so the h in the top and bottom cancel. And I get the limit as h goes to 0 from the left of just -2. But -2 doesn't change, it's constant, so that is -2. So that's going to be the derivative from the left. But then we notice that even if it were defined, and I didn't have that problem over there, these are still different values, right? So the left derivative and the right derivative don't agree, and so this thing wouldn't have been differentiable even if it had existed, okay? So again, in general, you check whether or not it exists, whether or not it's continuous, which this one was not, so it had already failed and I could have stopped there. But then if it were, just for the sake of completeness, doing out the rest of the problem, right, we did the right derivative, which is just taking the right-hand limit of the difference quotient. We took the left derivative, the left limit of the difference quotient, and we compared the values we got. Those also didn't agree, so this is sort of doubly not differentiable in some sense, all right? So that's that.